the first law of thermodynamics today. So I'll first do a recap of the previous class and then I'll start. Right, so we did this last class. I'll just do a quick recap of this. We saw that whenever you have an object, any material, it contains an energy within itself. The molecules have energy, and this energy is referred as the internal energy. And we found that this energy, which is the internal energy, is actually sum of all the kinetic energy that the particles have, plus all the potential energy that the particles have. Kinetic energy can be of three types. It can be the particles rotating, vibrating, or moving around. So rotational, vibrational, translational. Or it could be also potential energy, which is the energy stored within the bonds. Okay, so that's the internal energy. And we found that it's actually not possible to find the total internal energy for an object. It is difficult. I wouldn't say it's impossible. It's difficult because you can't individually know what the energy values are. However, it's very easy to find the change. So whenever there's an increase in internal energy, you can actually find that. And there are different ways you learn. One of them you learn in your O levels, the specific heat capacity equation, MC del T, that tells you how much internal energy is gained. And yeah, so that was, I think, the class before that. And last class, we saw that whenever you have a metal block and you want to increase the internal energy, there are many different ways that you came up with, but eventually they boil down to three main reasons, or two actually. One of them is that you can provide heat. So once you provide heat to your material, your object is at a higher temperature. So energy transfer takes place from a higher temperature to a lower temperature. That's one way. The other way, collectively, is called work done. So you can push an object against a surface. Friction will cause it to heat up. You can hammer it. Deformation causes it to heat up. Or you can pass current through it, where the molecules will collide with the atoms and electrons will collide, and there will be heat in effect. So essentially, there are only two ways in which you can increase internal energy ever. Okay, there's no other way other than these two, either by heating or by doing work on the system. Work can be mechanical work or electrical work. And this is the equation. So overall, you get one question from here once in a while. Questions are almost similar every time, but they will change around the way the gas is about the gas. How does the gas behave, right? So we'll see that in a minute, but this is the equation. Okay, it's change in internal energy can only be possible due to what? Due to increase in your heat or due to work being done, right? And yeah, so that's what we saw till the last class. So we'll start with this one. We'll dig deeper into this topic. So it's called the first law of thermodynamics. What does it say in our syllabus? You need to know that work done is pressure into change in volume, which I discussed last class. I'll derive this again and show it to you. And you need to understand the difference between work done by the gas and work done on the gas. This is something that we need to see. And recall and use first law of thermodynamics. They write the equation like this. There's a reason behind this. I'll explain in a minute. In terms of increase in energy, heating of the system, so it's transferred to the system, and work done on the system. Okay, so let's try to understand what this first law is. So the first law of thermodynamics is an equation. What is the equation? That if you want to change your internal energy, it can be done by either changing what provided to it, heat. Okay, so the symbol for heat is Q. Or you can also change the energy by providing work on the system. So there are two different ways you can increase internal energy. One is by applying heat. So this is heating. The other one is by doing work. So work done. And once you do that, you have a change in your internal energy. So internal energy increases because of this. Now, the thing is, if you do work on the system, so we'll break this down further, if heat is provided to the system, so you're providing heat to the system, Q is going to be a what value? Positive value. Okay, so if I'm giving heat to my system gains energy, right? So therefore, it's going to be positive. Now it can be written as positive Q or small q, and that's what they did here. So if you look here, they use small q, and small q is heat transferred to the system. So small q represents heat given to the system. It's an alternate version, okay? You need to know both of them. So you need to know that it's possible for it to be either positive q or just small q. I prefer that you learn the positive q. It's easier because we'll have numbers where you need to know plus and minus. And when it comes to work done, so if work is done on the system, so you're doing work on the system, you're providing energy to the system, right? So you can keep it plus W. Similarly, if heat is taken away from the system, instead of to the system, away from the system, what happens to your Q value? It's going to be minus Q. Okay, so a decrease. ওটার জন্য হলো capital Q use করা হয়, but we'll just use minus Q here. And this is work done by the system. So I'll give you examples of all of this. I'm just giving the values here. This is going to be minus W. So yeah, this is how it works. So essentially what's happening is that change depends on this plus this. Now there can be variations in this. I'll explain. So what if you provide heat of plus 100 and you do work by the system of minus 100? Can you tell me what should this be? 0, right? That means you'll find that the object doesn't change in temperature. If you hold the object, you'll find there's no change in temperature. Why? Because if there is no change in internal energy, there can't be a change in temperature, right? So this is going to be an indicator of what? Change in temperature. Change in temperature. So let's try to see this in practical example, okay? At question, just an example that, hey, let's say you have a surface like this, and you have a piece of metal block here. And what you do is you heat the metal block. So heat is provided to the metal block here. As you provide heat to the metal block, just heat, nothing else, okay? Can you tell me how would the equation look like? So, yeah, so you have del Q, del U equals to del Q plus del W, right? Can you tell me what would be positive here, what would be negative here, what would be 0? In your exam, that's what they ask. They'll not ask for numbers most of the times. Sometimes they do, but most of the time they'll ask for a plus, a minus, or what? 0. When it's plus, what does it mean? It's energy being gained, right? If it's minus, it means energy is given away. And if it's 0, it means there's no change, okay? So if I have a block here, it's a block, and I'm providing heat to this block. So, you know, I'm using like a heat source here to provide heat to the block. Can you tell me in terms of del U? So look into all three. It's a del U, del Q, and del W. So let's say we have del U here. তারপর হচ্ছে del Q and del W. So you just have to tell me plus, minus, or 0. So can you tell me if I take a block, metal block, and provide it heat, right? What should the values be? Yeah, del U is going to be positive. Why? Because, you know, it's going to heat up. You can actually feel the thing get warmer. So plus. What about del Q? Plus as well. And what about del W? 0. You're not doing any work on it, right? So it's just going to be 0. So that's the type of questions you get. And then, of course, what I provided you is like the most basic scenario out there. They'll probably never give this in the exam. They give you questions that are a little more, not complicated, but there are multiple layers to it, okay? And I'll show you another example here. So let's say I take this block, right? And I push it along the surface. So I'm pushing this along a surface. There's a lot of water experienced by the object because you're pushing along a surface, friction. And because of friction, I can feel that the block is slowly what? Heating up. So there's like a considerable amount of water acting on the block, friction. And the block starts to warm up. So if I touch the block, I find that it's warmer than before. Can you tell me if the circumstances are how it would be in real life? What would these values be? Yeah, well, del U would be what? Positive, very good. Because, you know, it heats up, you can feel it. Del Q? Positive. Am I heating the block? No, I'm not using like a heat source to heat it, right? So it can't be positive. It can be 0. So it's 0 to hold on. And what about the work done? positive because, as you rub a surface, it starts to warm up. That's work done positive. But turns out this particular question, right, will also allow another answer, which is this one is negative. And that is possible because if I take a block and I rub it against the surface, it warms up, right? And then it becomes warmer compared to the surrounding. Doesn't it become the heat source for the atmosphere? Do you understand what I'm trying to say? So if I take like a block here, okay, this block, I rub it against the surface, right? It starts to get very hot. And now, of course, U increases because now it has more internal energy. And that's because what did I do on the system? Work, right? But isn't it now warmer than the atmosphere? Shouldn't it start to lose heat to the atmosphere, right? It always loses heat to the surrounding. You know that whenever you have a hot object and the surrounding is cooler, doesn't a hot object start to lose energy until both of them become what temperature? Same temperature, right? So this will actually lose heat, and therefore the Q can be negative. Okay, but definitely what is going to be a higher value? The W, because initially you can feel the heat, right? Do you get my point? So the questions they ask will have these kind of layering. Like, it's not just one change, another change. It could be multiple changes. One could increase a lot, one could not increase much, right? So they'll ask you questions of similar type, okay? I will give you examples of it in a minute, but let's just go through that one more time, okay? তোমাদের question থাকলে আমাকে বলো. If you have any questions so far. The chapter is just, using the equation, nothing else. And questions that you get will be based on the equation, mostly on gases, okay? Like how gases behave. Yeah, so the table will also get warm. So that's also a place where the heat is lost. The block, yeah, that's the reason why this is positive. Why is this value positive here? Because there's what? Increase in temperature. The thing heats up, right? And why is this positive? Because what are you doing on the system? Work done. Work done is equal to what? The frictional force into the distance you have moved. No, we are like, so which object are you referring to here? The table or the block? The block heats up. Yes. So if I do this, right, would this object heat up? Yes. This is the system, correct? So this is the thing that we are focusing on, because if I did my whole question with context to the table, answers will be different, because the table will then have different energy system. So energy is transferred from one object to another, right? In this same question, if I took the atmosphere as my system, answers will be different. Okay. Can you guys predict what would happen to the atmosphere? So let's say the atmosphere, right? Can you give me the U, Q, and W for the atmosphere? So yeah, just a second. Yeah. Q হবে bolo? Yeah, U is going to be positive, Q is going to be positive, and W is going to be 0, because you're not doing any work on the atmosphere, but it's warming up. And it's warming up, why? Because the hot object that we created is heating the atmosphere right now. And you'll find this link here, which is interesting. You'll always find that if you take two systems together, they all balance out, because there's no net energy transfer. So you'll find that this is negative, and what is this? Positive, right? So the net effect would be what? 0, because one loses energy and the other gains energy, and the amounts must be the same. Okay. Do you understand what I said? So if my block loses 50 joules of thermal energy, right? How much thermal energy should the air gain? 50. But this is going to be minus 50, and the air is going to be what? Plus 50. And that's where the air will feel warmer right now, and the block will start to cool down. Okay. Right. So these are some basic examples. Now, just one more time before we write some notes on this. So the equation for first law of thermodynamics is this. This is the official version, right? But Cambridge has taken a turn here, or actually different bhabe jinishটাকে লেখে. So they will write this as del U is equal to Q plus W. And Cambridge হচ্ছে মানে তোমাদের সিলেবাসে this equation is mostly for gases. So this is change in internal energy for a gas. We'll see gases in a minute. Of gas. Q Q, small q is very particular, and I just mentioned this earlier. What is it? Yeah, positive. So it's heat provided to the gas, okay? So heat provided to the gas. And your W is going to be capital. What does the W stand for? Work done by the system or on the system? On the system, okay? Or work done on. Syllabus so I've put it up here. It's something very unique to Cambridge, okay? Cambridge, I mean, basically, it's normally not done that way, okay? So this is work done on the system. So yeah, that's the equation. So anytime, and listen, this is very straightforward. It's the first law of thermodynamics. There's the first thing that came to mind for people working on thermodynamics. So must have been the most obvious thing, right? Because, it's not the 10th law or something. So first law key wallet, that if there's an increase in internal energy, right? What does that mean? The kinetic energy, the potential energy is increasing, right? There are only two ways you can do that. What are the two ways? Either you provide what to your system? Heat. What does that mean? You place it next to a higher temperature object and your object heats up. Or what do you do on the system? Work, okay? There is no other way, absolute no other way by which you can increase internal energy. You can think of it. I asked you last class, there wasn't any way. You thought of many different ways. Eventually they turned out to be what? Work done. Like passing current is actually electrical work done. Hammering is mechanical work done. Friction is mechanical work done, right? So these are all work done. And the other one is heat provided. These are the only two absolute ways out there. So if anytime anything heats up, right, it's because of that. So example, okay, your body temperature rises. Can you tell me why? What's the science? Work done. Yeah, so let's say you have a fever and your body is now higher temperature, right? So how did that happen? Where you was work done on you, or was heat provided to you? Because you're clearly higher internal energy right now because your temperature is higher, right? What happens? Work done inside your body. Who did the work? Huh? White blood cells, no. Yeah, I mean they work, quote unquote, but that's like the fight infection. That's different. It's not like a paid work. But what's the other way your temperature increases? So what actually happens is the chemical reaction takes place. The chemical reaction takes place, releases heat, literally. And that heat is what your body is taking. That's what you are right now. You are surviving only because the food that you have taken in is been undergoing chemical reaction, and that process releases what out of it? Heat, actual heat inside your body, and that regulates your body temperature. Okay, the work done for center. And our example is, let's say your car breaks, right? And the brake pads in the car heat up. Why? Is that because heat is provided? We say it heats up, but is it because heat is provided, or is it because work is done? Work is done because the friction, basically the brake pads and the tire, they rub against each other and they create heat. They create so much heat that they glow red in, like, some cars, right? So do you understand, like, any place you can imagine of a temperature change, right? What is it attributed to? Either work done or what? Heat provided. So we'll do one more. The sun. What's going on in the sun? So is it del Q or del W? Work done. What work done? Huh? In the sun. Like, why is the sun hot? Why is it, 100 million degrees Celsius at the core? Yeah, so what happens is two very high energy particles collide, right? It's called nuclear fusion, and they release energy. And that energy in the form of heat. The particles basically have high Ke, and those high Ke molecules collide with the other molecules and they gain Ke. They collide and they gain Ke. So it's by means of contact. And what's that energy production or transfer by means of contact? Heat. Work done হচ্ছে না. Work done example হচ্ছে তোমার, আচ্ছা আমাকে একটা work done example দাও. Because most of these examples are heating, right? Can you give me an example of work done that makes an object heat up? Gas in a syringe. Decrease or increase? Increase. Yeah, that's a good example, but more practical. practical example. Yep, resistors as well, heater. Like, you know, the immersion heater, there's a rod that turns red. Why does it turn red and glow and give out energy? It's because what's passing through that coil? Current. And the electrons are colliding with the positive ions, and what do they release in the process? Energy, right? And that thing starts to gain kV, and it turns red and glows. And then energy comes to you by what means? Work done or heating? Heating, because, you know, it's now high temperature and the surrounding is low temperature, so energy is coming out from it by either conduction, convection, or radiation. These are the three ways of heat transfer, right? So yeah, that's it. And I'll give you an example, and then we will write about this. So example eta. I just want you to write down plus, minus, or zero in the boxes. So look at the question very carefully. There are very few questions on this topic. In the last 25 years, there are like 10 questions maybe, okay? So at the point, you'll find they're very repetitive. So it says that filament lamp is turned on and the temperature rises to 3000 Kelvin in the first 20 milliseconds. So you have a filament lamp here, you turn it on, and then the temperature rises to 3000 Kelvin. I don't know if you know this, but filament lamp core temperature, right, is actually almost the same temperature as the sun. Filament lamps, you know, the tungsten, right? It actually reaches 3000 Kelvin. Sun's surface temperature is 5200. So it reaches very close. And this happens in the first 20 milliseconds. Can you tell me what should these values be? So you should be what? Negative. Okay. How many of you think that you should be positive? Positive, okay. Why? Right, exactly. Temperature is the best indicator of internal energy, right? So for filament, I put here filament. So for the filament, it increases its temperature. So definitely internal energy must have gone up. So that's first. Who's responsible for this? Is it Q or is it W? Is it heat provided or work done? Chemical? No. Yes, exactly. It's work done by the what passing through, current passing through, and Q is going to be zero here. And I'll tell you why Q is zero here. Is because what time frame have we taken here? 20 milliseconds. 20 milliseconds is very small time frame, so it just starts to heat up. It's still not enough time for it to give out heat. So here, what happens is that your sorry, my mistake. Plus. Heat is zero and work is done. What is this work that's done on the system? Electrical work done. Okay, so this is the electrical work. Electrical work is electrons carrying energy, right? Electrical work. And heat is like no heat given. So no heat exchange in or out. And that's where you have a positive U value, and the positive U value is an indicator of increase in what? Temperature. So temperature increases. Now, question of power part. The filament lamp is now working at a temperature of 3000 Kelvin. It maintains this temperature. So you turn on the filament, right? It becomes 3000 Kelvin, and it stays 3000 Kelvin for a long time. Okay, because that's the operating temperature. How would these now look like? U is going to be what? Positive or zero? Yes, very good. Zero. Why zero? Yeah, it says temperature is constant. So it's not really gaining any internal energy or losing any. It maintains a constant value. But if this is zero, the other two need to do something, right? So yeah, one has to be plus, one has to be minus. Which one is going to be plus? Work done, because you're still providing electricity. But here's the thing. Why is the temperature not changing even though electricity is passing through your filament? Because whatever energy you're providing, that same amount of energy is right away being lost as what? Heat. And you put your hand around the filament, you'll start to see it's warm. So it's now heating the atmosphere around it. So it's going to be minus. Whatever the values are, it could be plus 1000. This is going to be minus 1000 because this is zero. And how do you know this is zero? Temperature is constant. Okay. So this is a very important indicator. So the examiner will question that where it says maintains the temperature, they'll write that. It means U is zero. That's directly, you can just say that, okay? Why is Q negative? Q is negative because heat is given to the atmosphere, right? So Q is negative because atmosphere is atmosphere, the surrounding is heated. Is work done ever negative? Yeah, when a gas expands, it's doing work on the surrounding, right? So this is lost, and this is going to be positive because electrical work is done on the system. Electrical work on the system. So this is going to be a gain. Because there's no net change in temperature, no temperature change, hence 0. Okay, so yeah, this is just an example. This is from a very old question paper, 20, maybe 6, 7, 8 or from time. I find this is a good question to start with. Okay, we have a few more later on that I would want to get, but this is an example. So do you guys have any questions from here? So yeah, at the end of the day, all you need to do is figure out whether it's plus, minus, or 0. Some questions will give you numbers. Okay, Tokun, you can actually do the math. And how do you find out the numbers? Work done, force into distance, electrical energy, QV, compressing or expanding a gas. What is that formula? E into del V, right? So that you'll have to apply. And the question will guide you through the process. We'll see a couple of those soon, okay? Correct. So you'll find the gas cools down, right? Right. So so far, this is the equation, and there's a note on the side. Copy project to So first law of thermodynamics. In the exam, if they ask for the first law of thermodynamics, you can either write the full definition or you can write the equation and describe what the words in the equation mean. Okay, so like del Q, del U, del W, P mean for it. Like, how can it be negative? Yeah, so let's say you have a gas in a container, right? And as it's compressed gas, and you let go of that container like a syringe, right? So what you'll notice, the syringe is going out. And as the syringe is going out, right, why is it moving outwards? Because the gas is expanding. So the gas is pushing the atmosphere outwards to expand, right? So it's doing work on the surrounding. It's pushing itself out, right? And when it does work on the surrounding, it loses its own energy. And that's why it cools down. If you took that same gas and you push it back in again, you're doing work on the gas now. So the gas gains the energy and it heats up. Yeah, but there's potential energy. Bonds to থাকবে. Negative heat. 0 Kelvin the lowest, negative minus. No, negative point degree Celsius, minus 273 degrees Celsius, which is 0 Kelvin. Kelvin scale was the smallest number possible. 0. There's no negative Kelvin out, the 0. It's literally called absolute 0. এর নিচে যাওয়া সম্ভব না. In which scenario? The filament lamp. So if electrical energy is causing things to work and heat up, that's just electrical energy. Between two atoms, chemical potential. Yeah, it's because of bonds. So if you go further in, chemical potential energy is actually just electrostatic energy. It's the plus and the minus of the atoms bind them together. No, electrical potential is different. When you have a plus and a minus, there's a difference in the potential current flows. That's called electrical potential energy. And the one that's in the bonds of the atoms, that's actually chemical potential energy. W can't be negative with current because current passing through it can only heat the system up, give it internal energy, it can't take it away. In which kind of scenario? Yeah, if there's a distance moved or if there's movement, then work is done, yes. Without movement, you can't have work done. Because eventually work done is force into distance, right? So there has to be a force and there has to be some kind of distance covered. Any questions from here? Right, so I'll give you a few more examples. All right, I think you understood this. I've added the note here to na copy korle cholbe, but they cannot. So what's going on here is yeah. So why are these like this? Like why is it plus 0 and plus, right? So when the filament is turned on, there's an increase in temperature, and this means that there's an increase in internal energy. So plus. How do you know it's an increase in temperature? You can see it. It went from room temperature to 3000, right? So that's why this is plus. Since electrical work is done on the system, this causes work to be done to be positive because you're doing electrical work on the system. Electricity is bringing in the energy, not taking it away. Okay. Also, it's a good thing to remember: electrical energy can only do positive work. There's no way of negative work with electricity, right? The filament did not get enough time to heat up, and therefore it didn't release heat. So Q is 0. 20 milliseconds is a very brief time. For you to lose energy, you need time. So that time hasn't come up yet, right? So that's why this is 0. But then once you wait for some time, right? Let's say you have waited for some time, you'll notice that the system becomes same temperature. There's a name given to this, instance when temperature remains constant. What do we call that? Thermal equilibrium. So the lamp and the surrounding have reached similar temperature. So once it reaches operating temperature, the temperature remains constant. So that means this must be 0 and the change must be 0. However, you're still providing electricity, right? So this is positive. So how is it possible that in an equation, something is equal to something plus something, and this is 0 and this is plus? Shouldn't that have to be minus, right? So naturally this has to be minus. So you get some questions where they're fill in the blanks, and that blank can't be answered directly. You answer it by looking at the other values. So if I told you like this is 500 and I told you this is minus 200, can you tell me how much is this? No. 700, right? Because 700 plus minus 200. Okay, so that's how you can figure this out. So that's how you find the gaps in your system. Okay, right. So I'll give you one more question, and then we are actually done with this topic. So, question past paper, but I'll redesign it for you. Question goes something like this. এটা তোমরা try করো, okay? নিজে থেকে I'll give the question to you first. So what is going on here? Observe. So you have water entering from the top. This is a water heater, by the way. And the water travels through the heater coil like that, and the water comes out from the other side. It's like you have a geyser in your home that works similar way. So geyser did different. There's like a container that has a coil, but there's some heating system where the water passes through a very hot coil. As it passes over it, what does the water become? Warm, right? So in this case, what happens is as the water passes over this coil here, it starts to get warm. So you have hot water coming out from here. And obviously, naturally, this coil is at what temperature? Very high temperature. Okay. Now, this particular heating system has water entering here at a rate of 10 kg per second. Okay. So the water that leaves here is going to be what as well? 10 kilogram per second as the rate at which the water is transferred. You need to find out those three things here. Okay. Del U, del Q, and del W for the water. So del U, del Q, and del W for the water. I'll give you some values here. The water enters here initially at 20 degrees Celsius. So that's the what temperature of the water, the initial temperature of the water. And the water heats up. And as the water comes out from the other side, the temperature is 50 degrees Celsius. It's like warm water, right? So you need to do math and figure out what is del U, del Q, and del W. Okay. This is a power supply that is on for 10 seconds. So 10 seconds is because if you keep your heater on for the whole day, obviously the amount of energy would be different, right? So for 10-second time frame, can you tell me what is the del U, del Q, del W? Okay. But information lagbe, I'm hoping you know this, but I'll still provide it to you. C for water. What is C? Specific heat capacity. Do you know the value? Yeah, 4200. We have this. This chapter is just based on this topic. Per degree Celsius. Yeah. So using these information, can you find del U, del Q, del W? This is for the water. And you'll also have to do the same for the heater. So heater del Q, del W, or del U for the heater as well. So give it a try. This is like a typical question that you can get. Only mark that. They give you 6 marks for this because there's 6 blanks out there. It probably will take 10 seconds if you're good at this topic. Like easy question. It's just a concept that's a little challenging for some students. So give it a try. Let's see Parmati. I've modified it slightly because when it came in the exam, there was other topics involved here. So I just took the part that you can answer right now. I'll add the question on the side so you can. Zero. Sure. Clear shit. 1.26 into 10 to the power 7. You got the same thing, right?
It's in joules.
Joules, right?
It's
Kilojoules. Yeah, I mean, that is possible. And so what are the values? So let's do this. Shall we try for can you tell me what's del U going to be? Is it going to be a positive, negative, or zero? Del U for the water. Positive. It heats up, right? Okay, clear. Del Q, is it going to be positive, negative, or zero? Positive, because you're heating the water, literally. It's called a water heater, right? What about del W? Zero, because you're not doing work on the water. Are you passing electricity through it? No. Are you hammering the water? No. Are you compressing the water? No, right? If you're not doing either of these, you're not doing any work. Sometimes students will tell me, but the water is flowing through the pipe. Isn't there work done there? Negligible. And that's gravitational work done. Water falling from a height, right? But that shouldn't hamper your answer. It's very negligible. Also, as the water passes through the pipe, wouldn't there be friction? Right? Wouldn't that also have like a working effect on it? So these are very negligible values, okay, compared to the amount you got. You got something like in the range of 12 million, I think, right? So it is a 50 joules of friction doesn't compare. Okay, done. For the heater, I don't know if you read the question. I have added few points. During the operation, the heater coil remains what? At constant temperature, right? So can you tell me del U, del Q, and del W for the heater? Yeah, del U is zero. Why? Because there's no change in temperature of the coil. Del Q? Yeah, minus whatever value you found, because that's the heat given out by the coil. Do you understand the exchange here? The coil gives out energy, and who gains energy? The water. And del W? Yes. And last the question at first, you find the power of the heater. Yeah. Yeah, right. Okay, so Guchadudumra, do you guys get an idea of what to do here? These are, I would say, medium difficulty questions. There are some challenging ones, but I'm going to pour it gas loss related. So first, what do we need to do here in this question? You need to find the del Q, the heat provided. What should that be? MC del T. What is the mass here going to be? 100. Do you know why? Because I said that the water enters at what rate? 10 kg per second, right? And for what rate or what duration am I asking you to find this? 10 seconds. So how much water would be entering? 100, right? So 100 into 4200 into your change in temperature is going to be 30, right? So 30. এটা কি অত বড় নাম্বার দেয়? 1.26 into 10 to the power 7 joules. Right, so that's the amount of energy that the heater gains or the water gains. So this is going to be plus that amount, 1.26 into 10 to the power 7. Can we write this as 12.6 megajoules? I think so, right? So I should have like do 12.6 megajoules. What is Q going to be as well? 12.6 megajoules. And work done on the water? 0. সবসময় তোমরা চেক করবা লাস্টে কি does this equal to this plus this? That's like the most basic check you can go through, and that will ensure whether you're at least right in terms of the addition part. Okay, there's a mark for that. Now look at this, very important. This heater gives heat out. This water takes heat in. How do I know that the water took heat in? Because it's positive. Whenever you're taking energy in, it's positive. Whenever you're giving energy out, what is it? It's negative, right? So if this is taken in heat from the heater, shouldn't the heater give out the same amount of heat? And if I get 10 joules from a heater and I take in 10 joules, doesn't it mean the heater gave out 10 joules? So what should this value here be for Q? Minus 12.6 megajoules, right? But we know that the temperature of that coil remains constant. U ki hota hai? Zero, because the U is based on temperature change, so that's zero. It only means that what is the work done on the heater plus 12.6 megajoule? What could this work done be? It's a key work done. Electrical work done, correct. So electricity is passing through the coil, and that's doing this, right? So the question is how to find the power. Easy. Power equals to energy divided by time. How much electrical energy was provided? 12.6 megajoules. Divided by what time did we take? 10, right? So this is going to be 1.26 megawatt. That is the power of a heater. Very unrealistic number. That's the power of a power station. So anyways, it's because 10 seconds at the temperature change is very unlikely. Okay, only a few degrees Celsius. If you ever turn on your geyser, it takes time, right? It's not instant. That's the reason. Okay, because it takes some time for water to heat up. Right. So I think this should be it. আমি এটা তাও পাশে অ্যাড করে রাখতেছি class is not over. I'll take a few minutes more. This is water. This is heater. Right, so why is it plus, why is it minus, and everything? I've added it here. I'll upload the notes. You can just go through it. If you have any questions, let me know. Okay. I don't get why the internal energy of a heater is zero. A very good question. Neither do I. I'll tell you why. Because internal energy of the heater is not zero. What is zero? Change. Okay, the internal energy of a heater is few million joules, maybe very large value, because there's so many particles inside it at high temperature, right? But the change is zero. And I think I discussed this last class in the class before. You can't find what the total internal energy for a material. It is very difficult. And the reason why it's very difficult is because there are so many different particles undergoing so many different combinations of movement. It's not possible for you to actually get a value. But what is possible is you can find the change, how much it increases and decreases. Okay, so that's what we can do. So yes, if the question was what is U, it's a question, I don't know. Okay, but if it's what's del U, we can say it's zero because the temperature is not changing. And why temperature change is an indicator? Because internal energy is directly proportional to temperature change, right? So if temperature changes, there must be change in internal energy. Ekhane ora bolche the heater coil remains what? Constant temperature. So there's no gain or loss. It's just constant. Okay. Right. So I've written this here in case you're wondering. It's just since temperature is constant, del U is zero. Again, short del. Okay. These are all del values. Right. So because we're done with the topic, I just want to go through this part one more time. The first law of thermodynamics, as mentioned in your book. So the increase in internal energy is what? The energy supplied by heating plus work done. That's the formula. The small q represents what? Energy supplied to the system. Okay, so I'll highlight these words here. And the W here represents work done on the system. And this is for a gas. So it says that for the first law of thermodynamics applies for all situations, not just for gases. The ones we did is for a random situation. Our syllabus focuses mainly on gases, by the way. We haven't done the gas laws yet. I can't really show you those equations, but it'll come to gases mainly. Okay, there is a sign convention here. So positive mane hocche increase in internal energy, heat is added, work is done on the system. So whenever you have a positive in front of your Q, U, and W, right, it means increase, addition, or work is done on the system. Minus money, decrease, taken away, and work is done by the system. So if you have like a syringe expand because of the gas at high pressure, work is done on the atmosphere, right? So therefore, your gas must lose this energy. So it's pushing it away. For which negative work done other than gases? Yeah, so you can use GP. So if an object is thrown upwards, right, that is an example of negative work done, positive work done. Positive is when it's going down, and negative is when it's going up. There's a little bit of a problem in this topic if we use GP because this is all molecules, like how molecules are behaving. But just generally, negative work done would be when you go against with the force. So let's say an object is taken from here to there. That's positive work done, right? And if I release it, it's negative work done. It loses that energy, gains Ke as an example. But I think I mentioned to him as well, when it comes to molecular level, negative work done is only easily visible by gases. So there's no negative electrical work done. There's no negative friction work done. There's no negative, compression work done. Those are all positive. Because you're applying force, you're doing work on the system every time. Okay. Right. So so yeah, this is basically the part that you have to be careful about. When a gas expands, W is negative. When a gas is compressed, W is positive because you're doing work on the gas. And when the gas pushes you out, it's negative. Okay. Yeah. So we'll come across this later on. I'm just giving you a heads up. There's a chapter much later on. It's called much later on, at least next week at ideal gases. That's where we apply these. Okay. On the next class data, ওটা হচ্ছে খুবই straightforward. I think I mentioned about this already. Thermometers. Okay, it'll take like 20 minutes to wrap this up, and then after that we'll start specific heat capacity and latent heat. No, gases. Yes. And then there's a reason for it. Yeah, so out of 10 questions that come in the exam, 2 of them will be non-gas, 8 of them will be gases. So the non-gas ones are the ones I have shown here by